Hello, everyone. My name is Marco Cecconi. I tweet at this handle here. It can be pronounced, but you can copy it, I'm sure. Anyway, so I work for Stack Overflow, and I specialize in working on the Q&A sites. So when you have a programming problem and you Google for that programming problem and you'll end up on Stack Overflow, you're probably running a page that I helped write. This talk is about how we put together Stack Overflow, what its architecture looks like. But more in general, is a talk that aims to explain to you what principles guide our architecture and how we got to this result. You will find many people that are going to tell you architecture X is the best architecture possible, or architecture Y is the best architecture possible. I didn't want to do this. I don't think our architecture is the best architecture possible, but it works really well for us. So I think it's much more useful if we concentrate on that, and we concentrate on how to get you to have an architecture that works well for you, for your specific, unique case. Does that work? Okay, there are jokes in these slides. You're required to laugh at them, please. Okay, so serious stuff. Architecture, so what is it? So architecture is the art of science or science of building. Specifically, it's related to building houses, right? And building palaces and temples. And especially habitable ones. So it's something that clearly existed since the dawn of time, since the first cities, but it became something studied and written about 2,000 years ago. These are the first books that we have on it. And finally, they already identify the three more important things that a good architecture should have. And these also apply to software architecture, so that's why I'm bringing them here. So the first quality that a good architecture should have is durability, right? You're building a house, you're building a palace or a temple. You don't really want it to fall down on your head while you're in it at the first rain or the first snow, right? So durability is very important. Equally, it's very important for a service or a website or an application. You don't want it to fall over all the time. The second quality of architecture is utility. What does that mean? It means that it does what it's supposed to do. So if you're building a house, make sure that you have doors so you can actually go in the house. And you haven't forgotten the toilet or you haven't forgotten the kitchen, so you can actually live in that house. Equally, if you're building a website, for example, make sure that the functionality of the website actually is there. You know, there are no bugs, but also all the functionalities that are needed are there. So this is interesting. This is the third historically known quality of a good architecture, that palaces or houses should be beautiful, according to some aesthetics, of course, which may vary across the years and the centuries. So how does that apply to software engineering? Well, it applies, right? So you're building code, you're building a big program, you're building a machine, and you want that machine to have some aesthetic qualities. You want it to be beautiful in some way. So that may mean a bunch of things. And you will find that most architectures actually, maybe not explicitly, but they identify beauty. So some of them may be identifying it in the magic word extensible, right? This architecture is extensible, or this architecture is scalable. These are all magic words, right? You know that they don't mean anything, right? They're just, you know, like beauty. They are personal opinions. For Stack Overflow, we decided to look for performance. So this is our criterion of beauty, of aesthetics of our architecture. So I looked up the definition of performance, and unfortunately, all dictionaries seems to be conspiring not to be helpful there. Definition of performance is ability to perform. But what we all mean about with performance is efficiency, right? So you build a website, you build an application, and you want it to be able to do what it needs to do with a minimum amount of fuss, materials, time, or energy. And interestingly enough, we decided early on that a good way to get to performant code was to use something similar to the scientific method. How does that work? So in science, and you don't have to read this slide, but that's what Wikipedia gives us for the scientific method. In science, you have a bunch of cycles and a methodology to actually derive models. What is a model? A model is a mathematical representation of reality. It's an efficient way of representing reality, right? So you could write a series of numbers that describe the position of all possible cars in a train and describe their motion, but you don't do that. You just give a formula to calculate those values, which is much more efficient. And how do you get to that efficiency is through this scientific method. In particular, I want you to look at this small blue-purple circle, the three-step circle. And that's the core of the scientific method. And what it says fundamentally is that you create a model, from the model, you create some tests, and then you analyze the results of the tests in order to modify your model. So there is this cycle. And there are two things about this cycle that are important. One is that it's data-driven, it's reality-driven. So it basically approximates the model to reality. And the other important quality that it has, it has that it needs to be fast, right? If each cycle of a scientific theory, each experiment takes 20 years, progress is going to be very slow. If each experiment takes 1 microsecond, then it's going to be really fast. Okay, so at Stack Overflow, we devised something similar. So we build code, then we measure everything. So we measure its performance, we measure its impact on the system, and then we analyze the results. What does that mean? It means that when you're building a website at scale, you have, if one experiment is like how a page is rendered for a user, you need to actually analyze the performance over millions of page views. And that determines how we build the next steps, how we build the new stuff. So, building something also as another thing which is very, very interesting is extremely important. So the first question is where do we start, right, to build something? And the first thing you need to understand is this. So you go to an architect and say, okay, I want you to build a church. Okay, can you do a plan of a church? The first thing they're going to ask you is that, okay, do you want this small roadside thing, yeah, or do you want a large cathedral? Yeah, how many people need to be in there, 0 or 20,000? That's sort of a slightly important thing. So let's look at the size of Stack Overflow and see more or less what kind of problem we are solving, and that contextualizes the architecture that we have. Otherwise, you're just going to tell me I'm crazy, right? So, okay, so this is a screenshot of a couple of months ago from a site called Quantcast. How many of you have used Quantcast before? No one? Fantastic. So there are two sites that measure page views or do ranking of websites in the world. Quantcast is one of the top 2. The thing with Quantcast, though, is that it groups results by domain name. And Stack Overflow is actually part of a larger group called Stack Exchange, which comprises more than 160 websites. And in fact, the rest of the network basically does the same amount of page views as Stack Overflow. So if you split up the domains, you're going to see all the performance, all the ranking, which is like half. But by adding together numbers, basically we can get sort of an approximation of where we are, and Stack Overflow is like in the top 20, somewhere between Wikipedia and PayPal, it varies about 10 positions across the year. But, okay, so that doesn't mean much, but it's really visited, right? Well, maybe, right? Because Quantcast is not very precise. So you shouldn't really trust it. And to give you an example of that, do you remember about North Korea, the country which has 28 websites? So they misconfigured the routers, and then we discovered that they only have 28 entries in the DNS. Anyways, so you can imagine them, right? Oh, internet. Yeah, according to Quantcast, they're looking at Stack Overflow, right? Number 1 in North Korea. Oh, and number 2, number 4, number 6, and number 9. Not bad. I somehow don't think that is true. But thank you. Okay, so these couple of slides have small numbers. I'll read them for you, don't worry. They're not very important. Anyway, so the network I was telling you, right? So we started with 1, with Stack Overflow, then we added the 2 more, Server Fault and Super User. And then we added more and more and more. When I joined Stack Overflow, that was 2013, I think, I started giving a version of this talk. And so that was about here, right? And we had around 100 websites. We were just crossing that threshold. And now we are here, and we are over 160. So it's a growth of what? Maybe, I don't know, 80%, something like that. That, of course, drives page views. This measured by Quantcast, again, not very reliable. So we started at like whatever was here, almost 0 in the beginning. And now we're, in 2013, we were around 400 million page views per month. And in September, when I did this, we were around 800 million. Actually, the number now seems to be 1.3 billion. So we grew about 2 or 3 times in the last 3-4 years. Okay, let's look at the web servers serving our stuff. Okay, so that doesn't grow, right? So we started with 1. Then we decided, okay, maybe it's a bit crazy, right? Let's have a little bit of redundancy. So we moved to 5, and then we had the 4 more, and we moved to 9. So we moved to 9 in 2011. I started giving this talk in 2013, and we're still 9. And now we are 2016, and we're still 9. So with the same hardware, more or less, same number of servers, we are serving 3 times as much page views, so 3 times as much load. So that's pretty good. And to give you an idea, I looked up the numbers for other sites up here. Where is it? Not in North Korea, here. Like Pinterest or Wikipedia. So we currently have 3 racks to host our website. So we have our own racks in a hosting company, and we have 3, so 3 columns, okay? Wikipedia has 30. And Pinterest instead uses, if I remember correctly, the cloud, and is between 500 and 1,000 virtual servers. So to give you an idea of what 9 means, it's a very, very small number. Okay, so how do we do that? So as I was saying, build, measure, analyze. So this is the fantastic 3 racks that we have. As you can see, they're not even full. There are a lot of drives up there. That's the biggie for us. Is not CPU power, is storage, right? We are a content site, so people answer questions and ask questions, and we need to store all that precious knowledge, and that requires hard drives. So there are a bunch of them. So after we build the hardware, oh, by the way, this hardware is Dell PowerEdge. As you can see, everything is configured by us. So we choose the kind of CPU, we choose the amount of memory, we choose the type and quantity of drives. We choose the brand of cables. We choose the brand of power strips. We choose everything in there is hotly debated and specified by our SREs. So a lot of build in there. So how do we measure this? We measure it in many ways. Interesting is this tool called Observer. This is a server monitoring tool that we have. It's open source. We built it. And it gives you an idea of more or less the amount of load that we have and the numbers, right? So these are the famous 9 web servers. As you can see, they're running between what? 4% and 13%. That's a pretty typical day. So we are running at the 10th capacity or 15th capacity. So that means we could have 15 times more load and still be up. In fact, that rarely happens. It basically never happens. It only happens maybe when there is a bug and we DDoS ourselves, which we have done multiple times. Or when someone actually tries to take us down, sometimes they manage to take down one of the machines. But as you can see, not only we are running on 9, but we could probably be running on 1. That is actually happened once, because we DDoS the other 8. Databases, similar story there. So we have 4 databases. This is SQL Server. There are 2 clusters. One cluster is for the network. One cluster is just for Stack Overflow, our precious unicorn site. So 2 clusters, SQL 01 and SQL 02. They think about Stack Overflow, and I think, and 3 and 4, yeah, 3 and 4, they are for the network. As you can see, both clusters really are not using CPU at all, or not that much. This is interesting, by the way. So this is not the disk size, yeah? This is memory size. So 700 gigabytes. But as you can see, we have space for growth there. So after we monitor all this stuff, what do? We crunch the numbers, okay? You don't really need to look at the details there, but these are our tables, and we want to know when we need to change the drives, right? Because they fill up. And so it's quite predictable. I mean, it goes with traffic, but it's fairly predictable. So we can plan in advance, okay, do we have enough for the next year, 2 years, 3 years, 4 years, enough disk space? And do drives exist that do what we want? For example, we want to do, to keep most of the stuff on SSDs. Are there good SSDs which are also the size that we need? It's not that obvious an answer. So, as I was saying, build, measure, analyze. This cycle takes about a year. So it's a very slow cycle, but it's there. So this is what the architecture looks like. So what's inside that rack that I was showing you? As you can see, your request comes from here. It goes through our edge routers and internet connection up here. There is a load balancer there. Actually, it's 2. One is active. The other one is just hot standby. That's not doing anything. And then these are the famous 9 web servers. And then there is some backend here. And the backend is comprised of a cache, which is very important. This is, I think, 2 machines running Redis on CentOS. And they do caching, and they do PubSub. PubSub is used, for example, to alert browsers when something is changing. So if you are on a question and someone has added an answer, you get a pop-up in real time saying, hey, there's a new answer here. And that is done through messaging through Redis and then back to the load balancers. Actually, that's done using WebSockets. I believe we have one of the largest WebSockets implementations in the world. We currently serve around 600,000 connections, concurrent connections. We have a search cluster running Elastic on CentOS. It's three nodes. to power the search, of course, and a couple of other things. We have the databases, which I already talked about, and here there is a service tier. This service tier is actually 3 machines, pretty beefy machines. And what they do is a couple of things. So the easy things is like they run or they invoke all our scheduled tasks. Right? We have a bunch of them, bunch of batches. They just go to the web tier and fire up some routes and invoke the scheduled tasks. But most importantly, they are a huge distributed index of our questions by tag. Our questions are divided by tag, or they are characterized by tags. And these things take a tag query of the form JavaScript, but not jQuery, and return a list of the newest questions in that thing, for example. I'm going to give another talk this afternoon. It's about how we build this and why we built this and how it works. It's very interesting, but very technical, so if you're interested. Anyways, so if you want to know more about our performance, you can go to this. It gives you all the details, pros and cons, stackexchange.com/performance. It tells you the machines, what they are, how many transactions per second we do. Hint is like almost 20,000. All this stuff. Anyways, so moving on. So how do we get this performance, right? How do we get stuff to run so fast and on such small hardware? So again, build, measure, analyze, right? So build, we write code, and this is an example of a classic, I would say, random class in our site. This is a class that powers our help center, which I will talk about later. A couple of things I want to show you in here, just to shock you a bit. There is a static class here, it's a static method. Global cache is something that basically wraps around .NET cache and Redis. There is a Lambda and SQL directly in the class. Also, this is our model and data layer and business logic layer in 9 lines of code. So this is the kind of code we write. But then we measure it. So when I go to the site or any other developer goes on the site, it sees this box here. And that is a tool called Mini Profiler. It's a tool that works with Ruby and .NET, which we wrote and is open source. What does it do? Basically what it does is it times parts of your code. So you can wrap parts of your code into using clauses. So using timers to start, whatever. And that times the code inside that thing, including the time of the inner calls, right? And if the inner calls have more usings in them, they create subtimings. So for example, here, as you can see, there is a tree of timings. And then what it does, it actually gives you the time, and it puts it on the page. So what happens is I browse the site, I see the result of an execution, how long it took, and if it's red, and red means bad, I can go and investigate why, where it stopped, what kind of things broke. In this case, this is interesting. This column here is detailing the amount of work that we're doing with SQL. And this is telling me that this is taking 12 milliseconds, which is, for us, is fairly slow. But mostly it's telling me that I have 3 duplicated queries in that execution. So the same query has been run 3 times. Probably it's an n+1 error. So I need to maybe go and fix it. Okay. Now, that data that I just showed you, again, small numbers, I apologize, is not only stored in the page for when a developer sees the page, but it's actually stored alongside the requests for a subset of the users, or all the users in some cases. And this basically means that I have a SQL server I can connect to. It contains all the logs from the web servers. And next to it, so in the same table, I have the timings of all the parts. So I can do stuff like give me the top worst performing pages for Stack Overflow in terms of number of SQL calls, or timing of SQL connection, or overall timing, and so on. So what I did once, so the most important page on the site, as you can imagine, is the question page, so the one that you land to from Google, typically. And so that's the one we optimize the most. And one thing I did is just for a tweet, I wanted to measure how our performance is. So this is just, select group by on that table. And this blue bump here is the total time, right? So the time to render the page, time to first byte. So this is 0 milliseconds, this is 50 milliseconds, and it's around 10 milliseconds. Probably here, around 1 millisecond, there is a bump because of some caching somewhere. There is another bump here. That is for outliers. I will talk a lot about outliers later on. But this is something that you want to make small. And this is something that you want to move left, right? So as small as possible. I think 10 is pretty fast. Other stuff that you can actually measure is how long it takes to actually run the SQL on that page. And again, a nice bell-shaped thing, around 2-3 milliseconds there, which is pretty good. That's why I was saying 12 milliseconds is pretty slow for us. That was probably somewhere here. And finally, the gray thing is Redis calls, so calls towards the cache. Fantastic. Redis is a fantastic tool. Do you know how fantastic Redis is? We throw all sort of crap to it. I mean, we never look at the CPU pretty much, because it's always like 1-2%. It seems like it's doing nothing, and its timings are like, in this case, like, okay, 1 millisecond for a few, and untimable for most calls. So it's like below 1 millisecond. So it's a fantastic tool there. So another thing, so here we go. So we write code in that crazy way. I will explain why we get there. We measure it, and we analyze the data. So we know, for example, that with this bump is here, we want to investigate why there are calls that don't work, and that leads to changes not only on the specific page, right, but it also leads to changes in how you generally write code, okay? So the other cycle that I showed you is a cycle that runs one every year. So it's a very slow cycle. But this one is a cycle of deployments, right? So you write code, you deploy it, so you can measure it. And this can be measured in terms of how many deployments do you do to production every day or every week or every year. When I joined around here, I was told that we were doing around 5-6 deployment per day, which was true. You can measure it, right? Because we deploy every time. So there are logs in our continuous integration system, when we deployed what. So I measured it. I sort of got a graph, and as you can see, we are pretty much stable. So as the code ages and the team changes and so on, we still manage to keep up the velocity of that cycle. And that's an important thing. I worked in places where you can deploy maybe every 3 months. And that's terrible, right? Because if you put in a bug, it's a disaster, because it's going to be in there for 3 months. If you make some wrong choices, you pay for it for at least 3 months, and so on. In our case, we can screw up, right? Because we can deploy straight away. In fact, when we screw up, when we put out tons of new code, what happens? This happens, right? So this is like how much variety there is per day in the deployment. And in August, we launched something, and that had a lot of bugs, a lot of work needed to be done, because it was a huge expansion. Do you guys know what it is? What is it? Huh? No. There was the extension that we launched is called documentation, and it's a new set of pages on the site where instead of answering questions and asking questions, you can document libraries. So for example, we have documentation for, say, C#, and it includes tons of examples on, say, you want to create a singleton class. How do you do it? There are four ways to do it. Some of them are better, some of them are worse. Which version of .NET are you using? Depends, and this is all explained there. So that was a lot of work. But I promised you an explanation about the code, right? So this is the Help Center. As you can see, the Help Center, what is it? It's a page, this is the index. It's got a bunch of sub-pages here in which we explain how the site works to users. So basically what it is a small CMS, which in read mode is basically a list of posts. And this is, the core of it, right? So this is how we get all the help posts out of the database. This powers every single page, but also powers the index and powers the backend interfaces to edit and everything. So this is like the core thing. And as you can see, it's maybe 10 lines of code plus 10 lines of SQL. So it's very, very simple. As you can see here, by the way, we use caching. This is key part of our performance, right? It's much better to, in this case, it's much better to just query all the pages and keep the whole lot in memory, and then just, query over that instead of going to the DB every time. So what we do is we use this global cache, which is a library that does a check in the HTTP cache of the web server. It's a standard .NET HTTP cache. If it's there, fine, it returns it. If it's not there, it tries to look in Redis. And Redis is like a distributed cache across the web server. So basically what it's looking for is some other web server already retrieved all the help articles. If so, fine, it puts it in cache and moves on. If not, it's the first web server to need this. So it's not in Redis, which almost never happens. And these are cached for a day. And so it will query the DB once a day, basically, and then fill up the Redis cache, so all the other web servers will see it, and then the local cache, so all the other requests on that web servers will see it. But it's interesting that this code is very terse, right? So it's really hard to screw up here. This is what I want to say here. It's really hard because, hey, this is a static method on the help post class. So the class has got the fields. The fields are filled here by Dapper, which is our micro ORM, which maps them to these column names here. And it's all there. It's like next to each other. People ask me all the time, oh, how do you manage the fact that if you change the DB, then you need to change the class, and then you forget which name is what? Well, because they're literally in the same file next to each other. That's how we don't screw up. So no data layer, no business logic layer, very, very compact. So we use cache. But we use cache also in very interesting ways. For example, here. So, right, this is one of the most important most important, hopefully not, but is one of the most upvoted answers on the site. Some poor bloke asked, how do you parse HTML with the regex? Does anybody know how to do that? No, you don't know how to do it because it's bloody impossible. The reason is the HTML is like weird, and you can do weird stuff. And like, for example, the HTML tag, you cannot close this if you want. So it's full of weird stuff. And so you can do it. So basically, this guy got upset, let's say. So the first, the answer is here. You can't parse HTML with regex. And then blah, 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 blah. He goes mad at the end, and Tony the pony comes. Anyways, so there were a lot of answers here, right? So you can see there's even paging for the answers. So if there is at least one answer, we give you a way of choosing the sort, right? So you want to see the most voted on top, or the newest on top, or the oldest on top. So that sort is basically a little bit of CSS and 3 anchors, right? 3 ahref equals whatever. So it's very, very simple, very, very static. There's no magic in there, right? Except there is. So remember that this page is special, right? This page drives 90% of our page views. So 1.3 billion, 3 billions per month times 90%. That gives you an idea on how many times this code is run. So how much is it worth to tune it? And so as you can see here, hey, what's that? It's a cache. Right? So we are caching these objects. What are these objects? So there's 1, 2, 3, 4 objects. These objects contain the data that's needed to render those tabs, right? They contain the kind of tab that is there, the label, a small description, a keyboard shortcut for JavaScript. So this is, notice that this is all static data, constant data, right? So once I create it, it can be the same for all calls. So, I mean, I'm not going to the DB, I'm not going to Redis, I'm not going anywhere. So why the hell am I caching this, right? Actually, caching takes more time than creating the instance. Does that make sense? So the reason why we do this is that, yes, it's true that this makes it slightly slower, but so local cache is just slightly bit different from the cache that I showed before, in that this one only stays in memory, okay? So we're caching in memory these 4 objects, basically. And the reason why we're caching in memory is that every page view that goes here can use the same, literally the same instance, and not a different instance. They get it from cache. They get a reference from the cache, and it's the same instance. So no memory is allocated here with this kind of code. Whereas if we take away the caching from here, we are going to allocate allocate memory for 4 classes every request. This is a lot of allocation, and especially is a lot of garbage collection. And this is the thing that you're going to hit as soon as you do game development, as soon as you do scalability or high performance in terms of websites. Garbage collection is a fantastic tool, but you need to know that it's there. You can't just abstract it away. In your imagination, you can say, I can just create classes and they go away. They don't go away. Okay, so a little bit about how garbage collection works. Who is familiar with the workings of garbage collection here? Come on, up your hands. About a third. So I'll go very, very quickly for everyone else. So basically what happens? There was C long time ago. In C, you have no garbage collection. So what happens in C? You go to the runtime and say, hey, runtime, I would like a new block of memory. Can you give it to me? Here's a new block of memory. Okay, I do what I need to do, and then I give it back. Right? So it's great, it's very performant, but your code has to remember which memory it is got so it can give it back. If it doesn't, then memory leaks, and it sucks, and your web server explodes. So I don't know when, but garbage collection was invented. And garbage collection, for example, in Java or in .NET, basically takes this away. So what it does is a bit like magic. So you create an instance instead of asking for memory. You create an instance, and that, behind the scenes, gets some memory from the runtime. And then there is a thread, which is called the garbage collector, which tracks or deduces which objects are still in scope and which objects are dead. And for the objects which are dead, it just destroys them and returns the memory back to the operating system. So it's like a magic thread that does cleans all the garbage that you created. That's why it's called garbage collection. So what it needs to do, though, at regular intervals, okay, and this is a simplified version, but bear with me, it needs to scan all the objects, starting from the roots, and sees which objects depends on which other objects. So it goes through and navigates all this tree of dependencies of objects and then marks all of them as alive, and the ones which are not marked as alive are dead. So, you can release all the memory, compact the memory, and then you get that. This is great if it's just something that happens in a background thread, right? The problem is that at some point, you need to have a stable tree in order for this to work. Otherwise, your tree walking is going to go haywire. And therefore, you need to block all the other threads. So at some point, garbage collection is going to say, wait a second, you just created 2 billion objects here. Give me a couple of seconds so I can clean them up. And so your users, all of them, at the same time, they will see a 2-second pause in the requests. Yeah? So that's really, really ugly for a website. So we don't want to have that. Or if you're playing a game, you see everything stops for 2 seconds and then goes again. So you don't really want to have that. In fact, for example, in games, the rule is no allocations at all during gameplay. When you start a level, you allocate all you need to do, you load all your assets, don't do anything, no allocations, and then at the end of the level, you can clean up. We can't do that because our level is like 24 hours a day, so we just need to create as few allocations as possible. So this is the reason why we cache this. And the reason why we use static stuff, because static stuff you have only one. But we started to have some problems at some point in 2013 when we decided to localize the site. And when we localized the site, of course, all the strings, which contain text that goes to the user, they needed to be to vary based on the localization of the site. So for example, we have a site in Russian. I don't know how you say active in Russian, but you can't just print active. You need to print active in Russian. So we introduced this function here, _s, which means localize that word. And this presents a problem because the return of this function here is going to be another string, right? A localized string. And that string is going to be an instance that is created. And it's created every time the page is run. So this would mean that we would have billions and billions and billions of localized strings everywhere. It's just not tenable. It's not going to work. So the two solutions for localization that are available normally are either fetch them from a DB or cache, or fetch them from resource files or cache. In both cases, you need to instantiate new classes every time. So this doesn't work at our scale at all. So what we did is we invented another way. And the other way is to go back as it was before we had this function called here, and basically make this function return literal strings. So I don't know if you're familiar with interning. Yeah, some of them interning, some of them what? Okay. So string interning is basically a trick, right? So strings are objects, but they don't follow the same law or the same rules as other objects. Because they are immutable, right? You can't change a string. If you look at all the methods on a string, they return a different string. So the string is immutable. And there is a mutable string, which is string builder, by the way. But the immutable string is the normal string, is this one. And this is for a reason. And the reason is that the compiler is smart enough to know the strings are immutable. So if you actually write a literal string, so like this V here is a literal string, it's going to be treated like an immutable object. So that means that every time someone goes to this page and he tries to use this string over here, the same instance is going to be used. So there is one copy of the letter V somewhere in the web server memory, and there's just one for all the requests. Whereas if you return stuff like this, the compiler can't figure it out, and therefore is going to allocate strings all over the place. And that doesn't work. So this is what we want to do. We want to go back to interning. And the way to do it is to create basically a huge switch on the language for each string, and then that switch returns the localized string, which is interned because it's literally inside that source file. So I'm going to give you an example. The problem was even a bit more complicated Because, for example, this is another string that we have. As you can see, the strings need to have parameters substituted in. And sometimes these parameters are numbers, and therefore the strings actually are more than one string, right? Because if you look at a singular string or a plural string, they're going to be different. Like if you say, I need to walk for one number meters, right? To use meter or meters, right? If it's 1 meter, you have to use meter. If it's 2 meters, you have to use the S. So it's basically 2 intern string in that case. So there were a little number of things like that. Like Russian, for example, has 5 plurals. Depending on the modulo 10 or something, it's super complicated. So all that stuff actually translated in code, right? So we can figure out which string to actually fetch from that switch. And that thing basically needs to be transformed somehow, so that underscore S needs to be transformed when the page is compiled into a call to something, right? So something which is static, like generated, this is generated code, underscore S, blah, 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 passing the parameters, and then requesting the page. So see, this is what .NET outputs when you compile a Razor page. It literally outputs all the strings as interned strings exactly for that reason. Because otherwise you're going to be in trouble. You know, if .NET compiler compiled with something which creates a lot of instances. So they do it, but we need to work with it. And so that call actually goes to a switch, right? So that call up here with the blah, 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 actually has a huge switch. This is the LC ID, the local ID of the thing, and this is the Russian version, for example. As you can see, it's like write this literal string, write a variable, write this literal string. Okay? This is just one. There is just one because it doesn't have any numbers in. If it had numbers, it would be combinations of things. So the interesting bit here is how do we do it, right? After all the strings are effectively in a DB, and nobody has time in his life to write a switch for each single string that we want to output, right? It's crazy. So what we did is we wrote our own compiler, right? We wrote a compiler based on Roslyn that outputs all the stuff. It pre-generates code, and it compiles all the Razor pages and the .cs pages, and output that code that you have seen. That's its output before actual compilation. And as a side benefit, this is the impact on our build times. We actually were able to be like twice as fast with that. Other things that we cannot do to explain the code that you saw is dependency injection, right? So this is one of the reasons why we use all sorts of static things. For example, this is an example of a dependency injection. What it does, it creates a custom object that returns your orders, for example, in this case. The problem with these things is that, again, they generate a lot of classes, so we can't use them. So we can't test. That's the problem. So we are in sort of in this situation, right? We basically don't have unit tests. We have 400 unit tests, and nobody ever runs them because they don't run really well. Because every call goes to the AB, for example. Right? Fortunately, we are a community of developers, so when we put out a bug, developers take pride in actually filing a bug report. How fantastic is that? No automated tester, no automated tests, but we have automated testers. This took probably, I don't know, 1 hour after we released the bug. But not only our users are great and they find the bugs for us, and they run in place of the automated tests, but they also take pride in finding the solutions to the bugs. So that's fantastic. I think you know, it's a way of how we adapted our architecture to our circumstance, right? We have a lot of developers in our users. Another important thing is not exactly the same cycle, but still a cycle that is there, is that we tend to hire people with a specific hacker mentality that are able to deploy and develop huge portions of the site by themselves, and they have this sort of mentality which is very practical, so the hacker mentality, right? We give them the best tools for the job, and then we let them code. So this is another cycle. So hackers, okay, so these are not the people we hire. They're more like this, actually. You know what this is, right? Yay. Steve. No, it's Bill. So we give them tools, right? 3 monitors is standard. How many of you have got 3 monitors? See, just 1 or 2. You should all have 3 monitors. It's better. And then the code that these people write is the kind of code that I was telling you about, right? We allow them to actually do the crazy stuff. Like, for example, write a compiler in your spare time. As you can see, it's actually something that works. And this actually leads us to be able to hire and retain more people with the same mentality, more hackers, more people who are good and take pride in what they do. Right? So people, tools, and code. So in conclusion, sorry I had to run a bit, but yeah, 0 minutes. Yeah, I know. So performance is a feature, not a luxury. So this talk was not very performant. But yeah, it's important for us if lack of performance is a bug, so we fix it. You need to have cycles. Cycles allow you to take something and shape it around reality. So it's an efficient representation of reality. And reality is the problem you're trying to solve. The results that you get very, very specific. In our case, for example, we gave up our tests because we have users that can test for us, but then the code is better. And they're extremely high value. I mean, for us, the buying web servers is just not a problem. It's just like a tiny 0.1% of our budget. We don't care about that. But ask that to other companies that have 30 racks. For us, and it's going to be for everyone, garbage collection is a pain. Then you need to hire the right people and buy them monitors. Right? Thank you very much.